Swayam Prabha. Digital India. Educated India.
Okay, this lecture I added based on the spectrum of the participants. Initially, this was not in the plan, but I felt that it is nice to cover these topics, at least for awareness. Special components of precast buildings. On our field visit, we had seen composite slabs, but many of you are asking like why they're putting props and all that stuff. That's why I will be talking about composite section. Then I will be talking about the walls, how walls are designed. Most of these designs follow the principles of conventional reinforced concrete. Okay. Next, the shear walls, corbels, deep beams, and finally, which was my original thought, tall buildings. But then I felt that it is not necessary to go into more details. I will be just giving you a briefing of a tall buildings. Now, regarding books, one of the students were asking, what are the books? Now, I strongly believe that if you are in the profession, you should have certain books. Maybe at least your company library should have. And if you're a student, obviously you should read those books. If it is not there in your library, tell your teachers to have it. The book by K.S. Elliott, Precast Concrete Structures, is a wonderful book which covers the component design. These are all the technical side. Okay. Stanley, Bachman, Tillman, again, it is similar that it covers the component design. Now, some of the topics that I'm covering today is there in the reinforced concrete design book, which we use as a textbook in our place. And then the codes IS 456 and the SP 34 detailing are in fact are applicable for precast members as well. Some special references I will come to the later. Composite section. Now, the way we are covering the composite section here in civil engineering, you can have several types of composite section. Steel, concrete, concrete, fiber reinforced polymers. Okay, but here we are talking concrete to concrete, but one is precast, one is cast in place. Okay. Now, there can be several types of innovations. What we see on the field was that they will have a precast base element, sometimes they call it a filigree element. Over that, there are certain lattice girders to have the composite action, and it also helps to lift it. And then they will be placing the concrete here. This next one is very common both in buildings and bridges, that you have a precast beam, and then you can have a cast in place slab. Okay, you can also have a precast slab. Okay, but then that's not composite. Okay, here this is the composite. Why I'm saying composite is that when I analyze this beam for the service condition, I will be considering part of the slab as the effective width. Okay, and in order to have that, we should have this shear connectors so that the composite action is achieved. Now, this is something, there are lots of variants. What we had seen in the BJ Shirke, essentially they are doing this, that they are having a a precast shell, which can be pre-stressed. Here I have shown a pre-stressing duct. Okay, and in that shell, they are pouring concrete. Okay. Now, these are certain photographs which I went to the site of Precast India Infrastructures Private Limited. Tomorrow, Kapilesh Bhate will be coming, and he will be talking about these projects. Now, in this data center, they are providing this precast beams, but then you can see that there are these shear connectors to have an emulative connection as well as certain composite action. Now, why do we go for composite sections. Okay. First, it's saving the formwork. Okay. That means when BJ Shirke was casting the slab, the precast part was acting as a formwork. It is considered a first track construction because you do not need much of props as you need for a conventional formwork, because a precast member is much more stiff than conventional wood formwork. Easy to connect the members and achieve continuity. That means in order to have the composite action, having the shear connectors is not a new thing. It is there for a long time. Okay. With adequate shear connection, this one I have highlighted in yellow. Any strain discontinuity at the interface of the precast and cast in place portions is ignored. Now, this is when if you do not provide the shear connectors, then you cannot say that they are composite. Then the slab will be just resting on it. It's a dead weight. But composite means that the slab or in a slab, the cast in place and the precast, they're acting together to carry the load under service condition. Now, for pre-stress composite section, the pre-stressing can be done in stages. Again, there are options. You can have pre-stressing in the precast. You can have pre-stressing after you have cast in place concrete. Okay. If it is in the cast in place concrete, it will be post-tensioned. If it is in the precast, it will be pre-tensioned. Okay. The grades of the concrete of the precast and the cast in place may be different, but typically they should be close enough. If they're not close enough, then the load sharing can be hampered. Okay. Now, if they're different, how do I analyze? We have learned this in our undergraduate that whenever there are materials of different moduli, we can use the transform section method, which we have already seen in the precast concrete. Now, the analysis here is presented for a pre-stressed composite section. The reinforced composite sections are even simpler. Okay, because since I had these notes from a pre-stress course, I thought why not to show them. Now, again, our idea is that we have to find out the stresses at transfer and service. But then the way you construct depends upon how you select what load comes. The analysis of composite section depends upon the type of composite. That means we had seen that there can be several options. Next, stages of pre-stressing. Okay, you have to know this as a designer. Okay, and the type of construction. Now, here I will be talking about the type of construction. Now, what is meant by the type of construction? The precast member can be shored or propped when the cast in place concrete is being placed. And that's what we had seen in the Shirke site, that they had propped the sections. Please note, the props were not as dense as conventional formwork. Okay. The following diagrams are a composite section with a precast web and cast in place flange. The pre-stressing, the web is pre-stressed before the flange is cast. This is just an option I have shown. If it is unpropped, then the whole the precast portion is carrying the weight of the cast in place concrete. Whereas if it is precast, then we are helping the precast to carry the weight of the green concrete. The precast itself is not carrying. Once the top concrete hardens, then we remove the props in a certain way so that it gains the composite action, and hence the weight of the cast in place concrete is carried as a composite section, not just as a precast section. Effective width calculation is given in this clause, which we covered in our undergraduate course. Now let's see the stress diagrams. This I said that is very important to understand what you are doing, to make sure that your calculations are right, to make sure the numbers that you get is correct. You should do the self-check. I'm repeatedly saying this. At transfer and after the casting of the flange, before it behaves like a composite section, the following of the stress profiles are there in the precast web. That means at transfer, if I am pre-stressing the precast portion, it will have a certain stress. That means Some of you were getting some weird stress diagrams. You have to understand that if they're flexural member, the pre-stressing will be eccentric, and hence there will be more compression at the bottom. There can be some tension at the top. Now, after the casting of the flange, then what happens is that if I am not, say, I am not taking advantage of the concrete at the top, then the effective pre-stress and the self weight is causing this type of, that means this will get slightly altered because the pre-stressing is dropping, and on top of it the cast in place weight is coming. Okay, I will skip reading this. Please read this in your spare time. Again, I'm strongly suggesting whatever handouts we are giving, please read them here itself. Once you procrastinate, you will never read. Okay. Now, once I have understood the stress diagram, then I can write an expression very similar to what we had seen in the pre-stress class. The first one is the uniform component of the pre-stressing. The second one is the varying component, and the third one is the weight. Okay, weight of the precast member. This is a transfer. Now, at the casting of the flange, this pre-stressing has dropped, and then the weight of the casting concrete is showing up in the third term. And why these are plus minus? You have to be careful. Whatever you are doing for the top and bottom, you have to select appropriately. Now, at the service, now here what I am saying is that I am going through these three types of construction. Please try to understand. Okay. And we are using the principle of superposition. Here in the service, please switch off your cell phone. Cell phones has to be switched off. We are using the principle of superposition because we are using a linear elastic theory. Okay. Now, for the type A construction, what happens is when the composite action has gained, that means that cast in place concrete has cured and hardened, we are removing the props, we are opening it for service. And now the service load, this live load moment, if I say, or even superimposed dead load, live load also includes superimposed dead load. This will be taken up by the full section. And now, if I want to compute the stresses, I will be compute the stress at the bottom of the precast, at the junction for the precast and the cast in place, and at the top of the cast in place. My stress diagram will be discontinuous. Please note, my strain diagram is continuous, but my stress diagram is discontinuous. Now, what we are doing is, now here we are adding the term for the live load, where we are now using different section properties. That these section properties are for the composite section, whereas the first three terms were the precast section. On the other hand, what is type B? Type B is if the slab only is supported on false work. Sometimes this is a situation in between type A and type C, that for the slabs we are providing props, but on the concrete that comes over the precast, I am not supporting the precast because I know the precast is stiff enough. Whatever concrete is coming on the precast, I am not going to prop the precast. Then what happens is that at the service, when I am removing the props, then the weight of the member itself, the precast and the concrete on the top of it, is taken up by the full section, and the live load which comes on the slab is also taken up by the full section. Okay, and the resultant will be similar. And this expression, again, if you note with the previous expression, it is slightly different. That now this, the cast in portion actually has come to the fourth term, which was earlier in the third term. If it is type C, the type C means if the precast web is also, that means the precast member also is propped. That's what we had seen in the site. during the casting, then the section behaves like a composite section even for the full weight of the member. That means the precast has its own stress diagram. But then when you're removing the props, the full weight of the concrete over the precast beam as well as the slab is taken up by the composite section. And any live load after that is also taken up by the composite section. And here also you please note, now again this the self weight has gone to this last term. Please try to see the difference between these equations. Now once you understand this construction procedure, you can write the equations by yourself. Okay. Now here, as I said, that I have assumed that the precasting force is acting on the precast web only, and hence the eccentricity of the CGS is from the CGC of the precast web. If you do post tensioning, then again you have to add some other terms. Okay, the post tensioning is for the composite section, and in bridge girders they will invariably go by what is called staged pre-stressing. Okay, pre-tensioning for the precast, post tensioning after the cast in place has been there. Otherwise, it is going to crack. In summary, that depending upon our sections, now I am introducing one term which is called the external moment acting on the web prior to the section behaves like a composite, because there I am using the section properties only of the precast. What are to be considered for the three cases? And what is MC? MC is the moment which comes when it acts like a composite section. What are to be considered for the three cases that has been listed? Additional stresses generated due to differential creep and shrinkage of the precast and cast in place portions. Now these are a bit more involved, that if you want to now calculate the creep effects, okay, then what to do? I'm skipping that. For the ultimate limit state, typically you can say that I will consider the full section with the lower grade concrete. That is the easiest. As a student, I would say just go ahead and do that. That means if the precast is M40, if the cast in place is M30, you say that as a composite section, it is M30. And then I will find out its ultimate capacity. That's the easiest. Otherwise, you have to use certain refined calculation to consider the different stress strain block for the M40 and the M30. Next topic is the structural walls. Now, this term is sometimes very loosely used in the practice. There can be different types of walls, and the way we classify them from the design point of view I have listed. The structural wall means they are load bearing walls. I cannot knock down a structural wall once the building has been constructed, unless the building is demolished. But for refurbishing, I can knock down what is called partition walls, which are non-load bearing. Hence, you have to be very careful that if you are doing some change in your, say, in your house, whether it is load bearing or not depends if there's a beam above the wall. Okay, that minimum check you should do. Now, if a structural wall is typically they are designed for gravity loads, but now if I'm designing a building for lateral loads, then I will design the walls for the lateral loads. If they're taking the lateral loads, then they're called shear walls. That means shear walls is a specific case of structural walls. What are infill walls? Infill walls are just filling up, covering the space. They are not even carrying any load except their own weight. Typically, we do not design infill walls. However, infill walls can be designed for lateral load resistance. And if you are using infill walls using what is called concrete masonry units, you can even reinforce them. And this type of technologies are there, that you take advantage of the infill wall, and so that you can bring down the cost of casting a concrete shear wall. Now, for a concrete shear wall, now I'm seeing a classification based on the method of construction. Cast in place concrete is the conventional. But in this course, we are focusing on precast large panel systems or wall panels. And this is a photograph I took when I visited to the site of the Timage precast in the Sri city. Concrete masonry units with reinforcing bars in the voids can also be used. But as I said, that this typically is covered in a masonry course and not in a concrete course. Now, if I'm trying to design a precast panels, the design equations that are given in IS 456 section 32 can be used. Now, in today's presentation, I did not load with the equations because many of you may not be familiar with this. Okay, but in case if you need them, at least today what I would say is that if you are having a copy of IS 456, at least stay aware of these sections. That section 32 talks about structural walls which are subjected to gravity loads. However, the code will not allow you to design exactly as the load acting at the central plane. It will ask you to design for an eccentric load, just like in a column, we design for a minimum eccentricity. Similarly, a wall is designed for a minimum eccentricity, creating out of plane bending. Okay, and for that, we should have 2 layers of reinforcing steel, period, because to take care of out of plane bending. Sometimes people think that if I just provide a single layer of steel, if my wall thickness is less, that is good. I would prefer no. Unless it is a partition wall, do not go by a single layer of steel. Now, coming to the precast wall, the challenge is not the basic reinforcement. The challenge is the connections. That's what Professor Liberato also said today. And here, first, I'm using the word joints because that's the way I have, I view it, that I am bringing the word more from the reinforced concrete design point of view. That wall-to-wall members can have horizontal joints, okay, where they are stacked up, and typically these joints in our country we go for emulative type, means there will be dowel bars sticking out, there will be a void in the top, and we have seen this in the Timage factory. And then once the top is lowered, you grout that space. Okay. If I look into the plan, now this is for a vertical joint. Vertical joint means that I am casting one panel like this, another panel like this. Of course, today Amit said that we should have much longer panels, and that's what they are doing. We shouldn't have so many joints. Then how do I connect vertically? It's like a zipper. Okay. We are having certain U-type bars or certain U loops, which photograph I have shown earlier, and then we grout the space, and if the space is large, we can even pour concrete. But this is one way of classification: horizontal joint versus vertical joint, and both these are considered to be emulative. But let me tell you, emulative does not mean it will behave like monolithic. That's a misnomer. At least this type of joint is weaker than had there been no joint. Okay, because the reinforcement is not continuous. Okay. In the vertical joints, I'm showing 2 types. One is the dry joint, which is more common in the Western countries. It is, this type of selections are also based on the climatic conditions. Okay, whereas we go for wet joints. In the dry joints, which Professor Liberato also showed, that there are embedded plates. Over that, we put another plate, and like that we connect it. Okay, and we can have some sealant or caulking material filling up the space. Whereas for the wet joints, we can have these reinforcements which are like transverse reinforcements. Either we can have U bars, either we can have loop boxes. The loop boxes are getting more and more common in our country. We can also have certain type of inserts to connect them, okay, which is not that common. Now, this is what I saw in the Timage factory when I went about more than 10 years back, that these are the loops which are available from the market, and they come in a box. These are flexible wares. You just have to put them on the side of the panels. When the panel is lowered, they do not create any obstruction because they can fold by itself. And then once the two panels are there, the two loops overlap, you place a reinforcing bar, you put a backing, some formwork, and do the grouting. On the other hand, you can have U-type bars which are already there in the two panels. You just have to bring the two panels together and the U bars are overlapping. Next, coming to shear walls. The shear walls are designed as part of the lateral load resisting system. And please note that our code IS 13920, at least those who are with the structure engineering background, you should be familiar with this code. The section 10 covers the provisions of shear walls. Here I'm not putting the equations, okay, but you, from your interest, you should be familiar with it if you are not already. The behavior of a shear wall, behavior means what? That under a certain load, first, how will it crack? Next, how will it yield? Next, how it is going to fail? This is the behavior. You're trying to understand the full picture. It depends upon the height to the length of the wall. If the height to length ratio is tall, then we expect, why I'm saying expecting is that if you goof up in your shear design, then it can fail in shear. But if the shear design is proper, then it is expected to have flexural failure, by which we can have certain amount of ductility. However, flexural failure also needs proper anchorage of the bars, and the foundation uplift should be checked. That means once the building gets taller, okay, these are the additional issues even for flexural design. Okay. On the contrary, if I'm having a squat wall, then it is primarily governed by shear deformation. That means the cracks tend to get inclined, and then the concrete may crush before the steel yields. It may be a brittle failure. On the contrary, there can be a sliding shear failure because we tend to have a construction joint there, and these are a different behavior as compared to the tall wall. Now, see, we cannot, whenever you go to a site, it's not that everything falls nicely in either of them. No, there can be walls which are in between. And depending upon your design, if you go to a site after an earthquake, if you're trying to do some diagnosis, it's very difficult sometimes to understand which was the fault. Either is it a construction joint issue? Is it a design detailing issue? This can be challenging to understand. Now, in terms of design, we can also try to classify the walls based on its horizontal section. The simplest type is a rectangular section, whereas what is preferred is, just like the way we go for I sections for a beam, similarly you can have a bounding columns. The bounding columns even may be inserted, they may be concealed bounding columns, but if you strengthen the edges, you get better behavior. Now, if I'm having walls in the perpendicular direction, then I can take advantage of the walls in the perpendicular direction as flange width of a certain effective length, and I can design my shear wall accordingly. Okay. And the core wall is like a box type. Again, you can do some more advanced analysis to take advantage that all these walls are together. The classification can be even another type. Now, this is called, the first one is a monolithic wall, where your say my1 formwork just goes up straight. This is the one which is preferred by the contractor, smooth finish even by the architect. But the second type is mostly used for a retrofit project, that you know that a building is not strong enough or stiff enough. What do? Then you select a bay and try to insert concrete panels. And once it is so, then it is called the framed shear wall. Obviously, the framed shear wall analysis is more difficult because now we have the interaction of the flexural frames and the squat wall panels. Now, if I look into the analysis, the flexural capacity of a tall shear wall with a rectangular section is given in IS 13920 in Annex A. Please stay familiar that this expression is there. If I am looking for the in-plane shear capacity for a squat wall, then strut and tie model can be used. Now, let me tell you what Professor Liberato, the way he's pitching at a very high level. And you can understand the way it is taught in the European countries. Okay. That's why if you say that, no, why do we need this? Don't say that. These theories are there. If you're going for postgraduate studies, please be aware about the standard. Now, these methods are based on the mechanics of two-dimensional reinforced concrete members. I'm not going into that. These are topics by itself. That how do you derive that expression in the annex for the flexural capacity? It considers a smeared layer of steel. What is a strut and tie model? Professor Liberato has given some hint. And today I'm talking about, again, the strut and tie model with some sketches for the next components. Next, in the corbels. Now, what are corbels? Corbels are like certain projections in the columns or bridge piers to carry the weight from the, say, the beams. Walls can have a bracket to carry slabs. Okay. Now, there are different types. The one on the right is a single corbel. There can be a twin corbel. You have already seen quite a few photographs. In a pier cap, this is the way it is. Just walk outside our campus and see the pier cap in the Sardar Patel flyover. Brackets, these are there for the walls, which can support hollow core slabs. Now, this is a schematic sketch. This is the figure I gave you in the first day for your tutorial problem. It's just a frame, one-way frame. And this is the corbels will support the gantry girders. Okay, that means you have to know the loads from the girders to design this corbel. For a bridge pier, that means the weight of the superstructure comes on this pier cap through the bearings. Now, section 28 of IS 456 covers the corbel, which is applicable for whether it is cast in place or whether it is a part of a precast column. Now, how do I define the corbel? I mean, how do I differentiate a corbel as compared to a cantilever? A corbel is a short cantilever projection. I have just quoted this from the code, where the distance AV is called the shear span. What is shear span? The shear span is the distance of the resultant load from the face of the column. Please note the resultant load need not be at the center of the two, because the code may allow a further eccentricity. This thing, whatever is being supported, it can move. Okay, that's why AV has to be estimated conservatively. And what is the effective depth? The effective depth is at the neck region. This is the compression point. This is the tension point. That means the effective depth is from the most compression section to the centroid of the steel. This is the conventional definition. Now, if the AV by D is less than if AV is less than D, which is obviously for a corbel, then we are defining it as a corbel and not as a cantilever. The depth at the outer edge is not less than 1/2 of the depth of the root of the corbel. This particular distance, whichever is a vertical, it has to be at least half of the total depth. The reason is, if you cut corner, then the concrete may crush. In a strut and tie model, one requirement is, since the concrete is under stress concentration, we need to have sufficient concrete around the strut to maintain it, okay, under the limiting load that you're designing for. Now, what are the possible failure modes of a corbel? Okay. First, the sliding shear at the interface. Now, this is a tricky issue, that you cannot have a construction joint. You cannot say that I will make the column flush and then bring the corbel and try to stitch it. Yeah, it is being done, In the bridges, they are doing transverse pre-stressing, but then it is costly. That's why what we do is we cast the corbel along with the column, although you are paying the price in the formwork level, so that you avoid this sliding shear failure. Next, yielding of the tie. This is the desired mode of failure. Whenever we are going to the factored limiting load, it is the steel should yield before the concrete crushes. Third is the crushing of the concrete, which will follow the yielding of the steel. And another failure can happen, which is the bearing failure. That means you can see that we learn all this in our undergraduate. Now, whenever you are a designer, you have to get this knowledge and apply it appropriately under these different situations. Now, the design procedure is what? The design procedure has to check all these 4 failure modes. Now, again, I'm skipping writing the equations. I'm directly going to certain aspect of this strut and tie. Now, this study was done one of my students, MTech students, to understand what is meant by the formation of a strut. It is a hypothetical model, okay, by the analyst for convenience. That is, before the concrete cracks, this is the stress flow. But once the concrete cracks, then it becomes a preferential material. It primarily takes compression, and then I need to have the steel to keep it in place. And at the failure, you can see that now the compressive stress path, or the principal compressive stresses, which can be shown as negative, is following a very narrow path from the bearing area down to the column. And based on this, you conceptualize the strut and tie model. In the earlier days, there used to be what is called some optical way of doing things. We used to have this photoelastic method. These days, of course, in civil engineering, we are not doing it because you can simulate that numerically. Okay. Now, this is the strut and tie model for a corbel. That means the load from the bearing, it is coming down to the column. Now, in order to retain the corbel in its position, I need this steel, but the steel doesn't have the development length. Hence, I need to bend the steel. That's a necessity. So once I bend the steel, there is change in the stress path of the bar, and hence there will be compression generated in the concrete. That means I'm not talking about the column load. Forget the column load. It's just the load supported by the corbel will create this type of stress path. And based on the stress path, you come up with a strut and tie model. That means what is the principle of a strut and tie model? First, you have to isolate this region, which is a disturbed region in terms of the strain distribution. As a free body, idealize the strut and tie model. Now, there are these days topology-based optimization principles, but for conventional things, we can guess. Okay. Design adequate amount of ties to satisfy the equilibrium of the nodes. That is, now we try to make this as a deterministic truss model. We try to get the forces, and once I know the forces in the ties, I know how much steel to be placed. And for the struts, I should make sure that I have enough area of the concrete which can sustain that compression. Also, there should be concrete surrounding it so that we can maintain the integrity of the strut. Detail the bars to satisfy anchorage of the ties and integrity of the struts. Now, this is the model which you solve. Okay, please note that there can be different types of nodes, and the detailing comes depending upon the type of nodes. The node A is having a compression, tension. It is called CCT. Node B is tension, compression, CTT. Okay, whereas node D is CCC. That means here in this model itself, you can see that there are 3 ways we are classifying the nodes. Now, this is a sketch I have taken from SP34. Please stay familiar with it. We teach this in our undergraduate course. Okay, that the main steel is this one, which has to be bent. Please note, it has shown that we have to give the development length from the face of the column. But then it also needs development length on the other side. But the corbel is short. Then in order to develop the stress here, I need to what is called weld this main bar with this transverse bar. Now this is an important thing which we do not do in a cantilever. In a cantilever, it has enough length to have development in its span, but here we do not have that length, and hence this welding is necessary. There can be another detailing where you weld this main steel with an embed plate on this corbel. Now this is more of a framing bar. Framing bar means a bar which is necessary to hold the stirrups. Okay. This distributed steel is necessary to check any sliding failure and also to confine the struts. In order to hold these stirrups, I need to have this framing bar. A lot of research papers have been done to come up with this type of like an optimum design. Now it has become a standard practice how to design a corbel. And this is a corbel which is only on one side. If you have a corbel on both the sides, then you can see that this reinforcement actually will go in both the corbels. Next comes the deep beams. Kondal Raj had done research on deep beams. To him, it will be nostalgic. Okay. Now, what are deep beams? Even this photograph I took when I visited Pune to see the factory of PIIPPL. Deep beams are large depth compared to the span. It can be used as transfer girders. What are transfer girders? Transfer girders are beams which support discontinuous columns. Sometimes they are called floating columns. Okay. They are subjected to high shear. Okay. They can come in also members like outriggers. Now, what is an outrigger? Let me skip right now. And spandrel beam means it's the beam which is on the edge of a building, which also acts like a barrier. Like in a car parking, you should be having a barrier for the cars. Go to our multi-level car parking in the research park. You will see that the barriers are a part of the beam. That means these beams are quite deep. You take advantage of the barrier, you make it an integral piece. Okay. There are present in stadiums, okay, industrial buildings and other non-building structures. Now, section 29 of IS 456 covers the deep beams. A beam shall be deemed to be a deep beam when the effective span to effective depth ratio is less than 2 for a simply supported case and 2.5 for a continuous. There are slight variants in definitions in the different codes, but that's not an essential thing. Finally, the analysis procedure is similar. This presentation I'm covering only for the simply supported beams. This can be extended to continuous beams. Now, the behavior under in-plane loading, please note I am saying that as if the load is only acting in the plane, there is no out-of-plane loading. Okay. For out of our precast members, today you have seen that for out of plane, you have to have some check, okay, that it should not fall out of plane. Now, the load behavior is dependent on the type of loading, whether it is a distributed load or whether it is a patch load. Distributed load comes from slab, patch load comes from supported columns. Now, whether the patch load is coming at the middle or the load can come at the top, that is desirable. You are mobilizing the full depth. But if the load comes at the bottom, that means you are hanging something like a sunken slab. Then you have to have hanger bars to pick up the load to the top. Or if the load comes somewhere in the middle, this can also happen. Length of the bearing, it's an issue. Presence of openings. This is also a requirement from the architectural point of view. Opening should be thought of a priori. Okay. And finally, it also depends upon the way you provide the reinforcement. This is what Professor Liberto also said, that you want to design the structure the way you want to behave, the way you want it to behave. Now, these are certain conceptual strut and tie models for the different types of loads. Thank you. If I'm having two loads, this is the way I can conceptual the struts, and I need the ties to hold on to the struts. If it's a single point load, then this is the way my strut and tie model is. The same models are also used for pier caps or say pile caps. Okay. Now this was a study which was done by Harshad. Again, what we try to understand is how the struts generate with the increasing load. Initially, this is the way the stress distribution is. Please note here you cannot actually see those plain sections remain plain type of situation. With increasing cracking, the stress gets concentrated. It tries to find the least path from the loaded region to the support region. If it's a distributed load, then we also have what is called an arch action. Now, arch versus strut and tie, it can be a mixed also. Now, there are energy-based principles to tell how much load is shared by an arch type, how much load is shared by a strut and tie. But typically, we keep it simple that under UDL, we will consider it to be an arch type formation rather than a direct strut and tie. Now, this is the detailing from SP34. What are the essential things? That for a simply supported, my steel has to be there, most of my steel, which based on this calculation from the strut and tie, has to be within a certain depth. However, I need some more additional steel like U bars to confine the support regions so that we have a good strut and tie action. Also, we need distributed steel throughout the height, not just for the temperature and shrinkage effects, but just for the struts to perform properly. We do not want the cracks to expand as the load is increasing. And to check the growth of the cracks, we need both horizontal as well as vertical steel. This is not as per the conventional shear design. This is because we do not need shear reinforcement theoretically. In your strut and tie model, the load is directly coming to the supports. But does it mean that I can totally get rid of shear reinforcement? No. I need reinforcement for the integrity of the struts. However, you can reduce the amount of reinforcement, say if you are using fiber reinforced concrete. This is the detailing near the bearing. Here they have shown that you need to provide proper development. For that, you need to have this horizontal hooks. Vertical hooks may be possible in a lab specimen, but in a large specimen, having vertical hooks will give a lot of clutter. That's why horizontal hooks are preferred. You may also have to increase the bearing area. The last topic is the tall buildings. Now, this is an area where sky is the limit. Okay. Now, there are very nice books. The Smith and Cole is it's a book published by UK, very nice for the beginners. The book by Mr. Taranath, I will be coming to about him in the last slide. Being a practicing engineer, he wrote wonderful books, and we should be proud that he is from India. Okay. There's a code on tall buildings, 16700. I believe it is under revision. Now, this code gives certain specifications for the analysis of tall buildings. Again, I am not going into those. This is not the forum to discuss, but those who are interested, you should be aware of this code. Now, in India itself, lots of exciting things are happening in precast. I am not talking only of precast tall buildings. We have already seen in the presentation of Mr. Amit Bardey that how much high-rise residential buildings are coming up. Now, this is of course a commercial building which has already been completed in Hyderabad, the Galaxy Towers, and this is the photograph during its construction. And you have to understand that with the development of tall buildings, we need to be aware of many other disciplines. The MEP, Mechanical Engineering Plumbing Services, the water lines, the wastewater lines. Okay, then the method of construction. Mr. Bardey was saying that how do you construct these tall buildings? Okay, the facades. Okay, the fire resistance. All these are topics by itself. That's why please be aware whenever you're in industry, you have to keep your minds open to be aware of these things. Now, this is the tallest building currently used with precast concrete. And you can imagine that it is competing with conventional concrete. Okay. Now, whenever we are trying to design a tall building, or I would say analyze first, we need to understand the components of a system. That's what I had covered in my second lecture. Okay. The vertical load is there at every second. Okay. What are the components? First, the load is generated at the floor levels. That's the heaviest components. There can be different types of floors. Okay. It can be one-way slabs, joist floors. It can be composite decks. Okay. Means steel concrete composite, which is quite common in the abroad. And there can be transfer slabs. Transfer slabs are equivalent of transfer girders in 2 dimensions. That means they're supporting floating columns. Beams, transfer girders, wall type beams, haunch girders, band beams. I'm not going to describe all of them. You can just, if you're interested, you can look into these terms. Columns, composite columns. Now, this is also a generic term. What BJ Shirki is doing, cast in place precast concrete. But we can have concrete filled steel tubes. We can have structural steel within concrete. Different types of composite columns are possible. Raker columns, columns which are inclined. Okay. Diagonal members, pilotis. Okay. Then the structural walls, which I just briefly covered, and finally the foundation. Now, in this course, I did not touch about the foundations at all. But my friends, this is the most important part of the building. We have a full course in our MTech curriculum, structural design of foundations, apart from the geotechnical courses. Okay. Now, the photograph on the left shows a transfer slab where that means you have a free space in the below the slab and the columns above are discontinued. Typically, these transfer slabs are pre-stressed. I mean, I would say they are post-tension. And on the building on the right, you can see the raker columns. That means these are also architectural features. You go to our Chennai airport and you will see raker columns. Okay. Coming to the lateral load resisting systems, it's not that the members are different. The same members now under this lateral load, how does it behave? The floors have to behave like a diaphragm. This is what Mr. DiBarretto was saying. The diaphragm design itself is an area. We talked with dry connections. In India, we do by a structural topic. Brace frames now from the floor, once you mobilize the vertical elements, how does it resist the lateral load? For small buildings, by frames. But then, as the building height increases, we need to supplement the frames. Otherwise, it's not stiff enough. We can have braces, mega braces. I will be showing you one photograph, and there you see in the buildings in Dubai and all, there are classic examples of using mega braces. Exoskeleton, that means the bracing system is outside the building. It's an exposed, it's a structural art. Braced core with cap trusses. Again, let me skip moment resisting frames. If you are having closely spaced columns, it is called a framed tube. Okay. And the framed tube will act together only when we connect them at certain heights. And those are called belt trusses. We can have a building made up of walls or dual system. Duals means both frames and walls. Concepts like tube in tube, bundle tube, these are the words which were developed in the 1970s when this tall building boom had come up. If you look into the growth of the tall buildings, it was championed in US. 1930s was one growth phase when the Empire State Building and other buildings had come up. Then there was the Depression, World War, and again in the 70s it picked up. And there this new structural system had come up. Space truss, diagrid system. I did not load this with photos because we don't have the time, but again, you can Google it, and just for your awareness, you can stay aware of what these terms mean. Now, this is what is happening throughout Indian urban landscape, that we are going for shear wall type of buildings. These are all like Maiban formworks which grow. And on the right, you can see this building. When it came up in our neighborhood, it was quite an iconic building, the Tidal Park. Now, of course, you do not get this view because lots of other buildings have come up in front of it. And here you can see that these are the mega braces, and how nicely you can integrate that along with the facade. Now, coming to the analysis, obviously, it needs patience. Right? You have to understand the way you have to develop the model. This I got from a project in Gurgaon from Professor Meher Prasad. The beams and columns are modeled by frame elements. This is I mentioned in my first course on the, this is what the basics we have covered in our handbook, how you model the slabs, the shear walls, the foundations. Okay. Now, one important thing comes in tall buildings is the wind tunnel analysis. Now, the Structural Engineering Research Center has a state-of-the-art wind tunnel facility. There is a company called RWDI, which is a Canadian company, now has opened a office in Thiruvananthapuram. IIT Kanpur has. That means if you get an opportunity to see a wind tunnel, how they are doing. In our campus, we of course have a wind tunnel for the aerospace department, but not for the civil engineering. In wind tunnel, you try to generate the landscape, okay, and it is called a boundary layer type of studies, so that you try to mimic what can happen due to the interference effects. I'm ending this, my presentation, today is my last presentation. I ending this with a few pioneers of tall building. Fazlur Khan was from our subcontinent. He studied in Bengal Engineering College, did his PhD from University of Illinois at Urbana-Champaign, and used to work with a company called Skidmore, Owings and Merrill. He is considered to be one of the greatest structural engineers of all time. He came up with these concepts of frame tube, bundle tube, okay, and this is building he had built, this tallest building during his lifetime, which was called Sears Tower. Now it is called Willis Tower. This is of course of structural steel. The building in front was also designed by his company, which is the tallest concrete building at that time. Now, Fazlur Khan used to speak a lot about this structural art, but they talk in a different plane, okay, in the professional gatherings. To quote, the technical man must not be lost in his own technology. He must be able to appreciate life, and life is art, drama, music, and most importantly, people. His friend and close associate, Srinivasa Hal Iyengar, is from College of Engineering Guindy, then IIC Bangalore, and they used to be called Hal and Faz. He also was involved in these buildings. I am just showing another building which was done by this duo. This is the John Hancock Center, and here you can see that the exposed mega braces, they give the stiffness of this tall building in this windy city of Chicago. Okay, there are many other, you can just Google them and you will be able to know about them. B.S. Taranath, his book I was talking about, he used to work in Houston. I really appreciate that being a practicing engineer, the way he has put this material in the form of a book, which is extremely helpful for the professionals. Joseph Polacco, he was also from the University of Bombay. He used to work in Houston, but I think they are all now very close to aged. Okay, and he has also designed many buildings in India, in Mumbai, and this is one of his creations. Thank you.